Hello everyone, in this second video I'm going to talk about how you evaluate the performance measures of the KNN algorithm. To evaluate the predictive performance of the KNN model, we can compare its performance measures to a naive rule. In the naive rule, all cases are classified into predominant class. When you look at the results here, you will see that with KNN algorithm, you have 149 cases are correctly classified in the target case and 12 of the cases are not correctly classified as target case. So it's a total of 161 cases. Because there are 161 target class, which you see from the confusion matrix, and our target class is enrolled in the gym, among the 399 validation data cases, the predominant class in this case is not enrolled or non-target class. Therefore, the naive rule would classify all cases into non-target class or do not enroll in the gym and produce an accuracy rate. Let's calculate the accuracy rate. Remember, we have 399 cases in the validation set and 161 of them classified as target case. So the remaining is the non-target case. Therefore, we will have an accuracy rate for the naive rule is almost 0.5965. And sensitivity is going to be 0 and specificity is going to be 1 with the naive rule. So the accuracy rate with the naive rule is going to be 59.65% and sensitivity will be 0 and specificity is going to be 1. The reason is because naive rule classifies all of the cases into the predominant case, which in this case it's do not enroll or non-target class. Therefore, the KNN model shows better predictive performance than the naive rule does, especially if the goal is to identify the target class cases. So, the choice of the cutoff value can influence the confusion matrix and the resulting performance measures. By default, that what we have used to calculate the confusion matrix, R uses 0.5 as the cutoff value for binary choice models. The analyst may choose to increase or decrease the cutoff value to classify fewer or more observations into the target class due to asymmetric misclassification cause or uneven class distribution. So what do we mean by asymmetric misclassification cost? In this example, just think about the opportunity cost of missing a potential gym member who would have purchased a gym membership and a potential customer who ends up not purchasing. So for a data analyst working for this gym membership, the most important thing is to catch the people who ends up buying the gym membership. Therefore, the opportunity cost of missing a gym member who would have purchased a gym membership is likely to be higher than the cost of reaching out to a potential gym member who ends up not purchasing a gym membership. And besides, when you look at this data set, out of 1,000 past open house attendees in the data set, 403 of them purchased the gym membership, suggesting that the probability of an open house attendee purchasing the gym membership is, we can calculate here, 403 divided by 1,000, and this is close to 0.4 instead of the cutoff probability of 0.5. In this case, you as an analyst may reduce the cutoff value to a lower value than 0.5 in order to classify more cases into the target class in order to achieve a higher sensitivity value. So we go back to the R code. To evaluate the predictive performance of the KNN model using a different cutoff value in R, we first compute the probability of each case belonging to the target class instead of its class membership. In the predict function, we set the type option equal to prop to predict the probability values. So we are going to enter here KNN class prop is equal to predict and then open the parenthesis KNN fit new data is equal to validation set. We are going to use the validation set and then type is equal to prop and then control enter. So let's see what KNN class prop looks like. Control enter and you can see the probabilities on the console pane. And from this table, you realize that the first column lists the probabilities of the cases belonging to class 0, not enrolled in the gym, while the second column lists the probabilities of the cases belonging to class 1, which is enrolled in the gym. To determine the class membership of cases using a cutoff value other than the default probability of 0.5, let's say we are going to use 0.25 in this case, we compare the values in the second column to the new cutoff value. So our focus is the target case, therefore we are going to compare the probabilities in the second column to our new cutoff value of 0.25. To construct a confusion matrix using the new cutoff value of 0.25, we use the if-else function to determine the class membership. We use as.factor function to convert the class membership to factor, which is the same data type as the target variable. In our case, our target variable is enroll. Now let's type our command, confusion matrix, in the parentheses as.factor, and open the parentheses, if else, and if our KNN class prob, and we take the second column, and if that second column probability is greater than 0.25, then 1, otherwise 0. And then validation set, we choose the enroll column, and positive is equal to 1. And then control enter. So you see the resulting confusion matrix on the console pane with the cutoff value of 0.25. So accuracy rate is 0.9073, sensitivity is 0.9689, and specificity is 0.8655. Although the overall accuracy is lower than before, the new cutoff value allows you to identify more target class cases correctly as signified by the higher sensitivity value. To create a cumulative gain table and a cumulative lift chart, we need to convert enroll variable back as a numerical data type as required by the gains package. So we are going to first convert enroll variable, validation set, and we choose the enroll, and then as.numeric is going to make this transformation, and again as.character, validation set, choose enroll, and control enter. We generate the cumulative gains lift table using the gains function. The gains function requires two arguments, actual class membership and predicted target class probabilities. So let's create gains table here is equal to gains function, and then validation data set, and choose enroll. This is the actual one. And then our predicted probabilities are KNN class prob, and the second column from this, and then control enter. And let's see the gains table. Control enter. Yes, you can see on the screen the gains table for this dataset. By default, the cumulative gains table divides the cases into 10 groups based on their probabilities of belonging to target class. The last column shows the average probability for each group, and these values are rounded to 2 digits after the decimal point. In R, in situations where there are less than 10 possible probability values, the cumulative gains table and decile-wise lift chart will show less than 10 groups. Next, we use the plot function to create the cumulative lift chart. The first command plots the lift curve for the KNN model, and the second command draws a dashed diagonal line to indicate the baseline model. Let's use plot, open the parentheses, C, 0, comma, gains table, and from gains table we want cumulative PCT of total times sum, validation set, enroll, and then C0 gains table, and then we choose cumulative observations, and then xlab is equal to number of cases, ylab is equal to cumulative, main, the title of this graph is going to be cumulative lift chart, and then next type is a line graph, and that's it. And next one is lines C0. The second one is going to add a baseline scenario, some validation data set, and we choose the enroll here, and then C0 dim validation set, and here we are going to choose the first one, and then color is going to be red, and then the next one LTY is equal to 2. Here there is one parenthesis, and the parenthesis is going to be deleted from here. Let's control enter. Now you can see the cumulative lift chart under plots pane. To plot the decile-wise lift chart, we use the bar plot function to plot a bar chart. And let's type the function bar plot gains table, and we are going to choose mean resp divided by mean, open the parentheses, validation set, and enroll, and then comma, names dot arc is equal to gains table depth, and then xlab is equal to percentile, and ylab is equal to left, ylim is equal to C03, and main, the title is decile wise lift chart, and then control enter. The decile wise lift chart is displayed under plots pane, and this chart shows that if the fitness center contacts the top 22% of the potential gym members with the highest predicted probability of enrolling, the gym would be able to capture almost 2.3 times as many potential members who actually purchased the gym membership, compared to a scenario where the fitness center randomly selects 22% of potential members to contact. The KNN model shows superior predictive power compared to the baseline model. And finally, we are going to plot a ROC curve. We use the ROC function, which produces a ROC object that can be used to plot ROC curve. We then use the plot.ROC function to plot the ROC curve, and AUC function to retrieve the AUC value. So first let's create the ROC object. ROC.object is equal to ROC validation set, and then choose enroll from there, and then KNN class prop. Again, we are going to choose the second argument here, and then control enter. Now we are going to use plot.ROC, control enter, and we will use AUC ROC.object for the AUC, control enter, which is area under the curve is 0.9467, and this is very high, and that indicates the KNN model performs extremely well in predicting the gym enrollment among potential members. You can also see the ROC curve under the plots pane. The KNN model performs better than the baseline model, gray diagonal line, in terms of sensitivity and specificity across all cutoff values. So this is how you can evaluate the performance of KNN algorithm. Thank you for watching this video.